Hi, and welcome to Lab 3, Magnetic Field of a Bar Magnet. So before we begin, let's go through some introductory items. The purpose of this lab is to explore magnetic fields and their relationship with distance using a bar magnet. Some fundamental concepts we're using in today's lab is the Biot-Savart law and the magnetic field of a bar magnet dependent on distance. Some assumptions we made during this lab were to assume that the bar magnet we're using acts as a magnetic dipole. And some of the main results we got was that the magnetic dipole moment is 2.2 amperes times meters squared, and that n is equal to negative 2.5. So beginning the experiment, our system was the bar magnet, our surroundings were everything else, and then our initial conditions consisted of the bar magnet and the magnetometer. So first we had to set up the magnetometer, so the phone was slid horizontally until we found the maximum x value, and then we placed some tape on the phone as a placeholder, and then we slid the phone vertically until we found the maximum y value, and then placed another piece of tape perpendicular to the other, and then the intersection of that tape, the top corner, was the location of the magnetometer sensor. Now we were finding the on-axis component, so we had multiple data points measuring distance from the bar magnet to the magnetometer using different magnetic fields. This data was then linearized using the below natural log equation and then graphed. And then we had to find the off-axis component, so we used the on-axis distance and we slid the phone in the same magnitude but in the vertical direction. Then we recorded the net magnetic field at this location, and then to find the bar magnet's y component, we took the total y component, or total net field, and subtracted the Earth's total magnetic field in the y component. So to create this computational model, we used GlowScript. First, we created the magnet at the origin and had the magnitude of the magnetic dipole moment. Then we created the magnetic field, on axis and off axis. We had 6 observation locations, 2 on axis and 4 perpendicular. And then we had arrows for every magnetic field on axis and every magnetic field off axis. Then we created an average perpendicular distance and found it 45 degrees off axis. And we also had an arrow associated with that. So this is what it looked like when we were done. And here is the magnetic field of all the on-axis and off-axis or perpendicular arrows. And then we found the magnetic field at distance d, which was 45 degrees from the origin. So now we are going to compare the experimental data and the computational model. So the data varied slightly, but they were still within the same order of magnitude, which is somewhat accurate. Our experimental off-axis field was 6.4 times 10 to the negative 5th Teslas, whereas our computational off-axis field was 2.7 times 10 to the negative 5th Teslas. So our experimental data was prone to more error and real-world effects, whereas the computational model was coded in perfect conditions. So what if I hadn't oriented my experiment to compensate for magnetic north, and instead had my meter stick at some random angle with respect to Earth's magnetic field? So this would have skewed the data a lot more, since Earth's magnetic field would interfere with the bar magnet readings. That's why we had to orient it towards magnetic north. And so what if we were to stick 2 identical magnets together and do the experiment again? So the measurements should in theory double in magnitude but stay in the same direction, because it would just become one big magnetic dipole with north and south in the same direction. So some conclusions of this lab are possible sources of error could be found in handling the phone, and that could have interfered with some of the magnetic field readings. I could have misread measurements from the meter stick. That could have also messed up the calculations. And lastly, the bar magnet I could have used may not have been a strong enough magnet to act as a magnetic dipole. The results of this lab include that a bar magnet can accurately act as a magnetic dipole, since the experimental and the computational data were relatively similar, and that distance is an important factor in determining the magnetic field of an object. Thanks for watching.